Thank you for watching this video. Now we have, I believe, video 5 in our Circuit Protection Fundamentals video series. 11.5b, EFuse versus Fuse. So why not use a fuse? Well, although they provide protection, they tend to be slow, very inaccurate, very lossy, and they are designed to fail. After they do their job, the load is unpowered and will remain unpowered until somebody fixes it. They are also quite inaccurate. If we look at this fuse plot, the black zone represents where the fuse may blow. On the horizontal scale, we have time. Over on the right is 1 millisecond. And then we have 10 milliseconds, 100 milliseconds, and a second. And vertically, we have a normalized current, which is the fault current over the rated current, or the current at which the fuse will blow, divided by the rating of the current. So if we assume this is a 1 amp fuse, we'll normalize the 1 to 1. If we want that fuse to blow in 10 milliseconds, it's going to take somewhere between 2 and maybe 6 amps for a 1 amp fuse to blow in 10 milliseconds. That's a lot of current to be drawing for 10 milliseconds if there are other loads on the bus or if it's a marginal power supply. And as you can see, if you want that fuse to blow in 1 millisecond, it can take up to 15 times the rated current. Whereas we look at an EFuse, if this is our normalized current where we want it to blow, it will always blow within this green range. So the EFuse is A, far more accurate, and B, will not allow nearly as much power to be drawn from the supply during an overcurrent event. This can be beneficial for many reasons. One, it protects the power supply. 2, it protects the load. And 3, it can protect other devices that are connected to the bus from suffering resets due to bus droop. So time and trip limit accuracies mean bigger power supplies. If you don't want the bus to droop during these events, then you're going to have a power supply that can handle much higher currents. It will have to have much higher margins to keep the bus up and within spec when one of the loads misbehaves and draws too much current during an overcurrent event. As we saw in the last slide, fuses are slow. We can look at, and this is for a fast blow fuse. If we want that fuse to blow in less than 3 milliseconds, the only way we can guarantee that is if the load current is at least 10 times the rated current. So iLimit with an EFuse, it's programmable, very predictable, stable over temperature, and bus droop and supply stress are reduced because of this tight overcurrent tolerance. Fuses are also very lossy. This loss, which is due to higher resistance, means more energy is burned even when everything's running properly, and that's more heat and higher operating expenses. We did a comparison, and it was a 2 amp load. The 2 amp fuse dissipated 13 times more power than the TPS 2590, which is a nominal 30 milliohm R-on. Now, we have heard varying numbers from different customers, but the lifetime cost of a watt is anywhere from $2 to $18. This includes the energy cost itself, distribution infrastructure, heating, ventilating, air conditioning, and just the cost of heavier buses to carry the heavier currents. And this is over the entire expected lifespan of the device. So here we can see a 2 amp fuse is nominally dissipating 3 amps at the rated power. Let me go boop. And if we plug in equivalent dissipation under the same conditions for the TPS 2590, instead of 3 watts, we've got 120 milliwatts. And as we move up to higher currents, we have 3.6 watts versus 3/4 of a watt for a 5 amp device. That's still very significant power savings, especially when integrated over the lifetime of a part. Fuses are inaccurate. The manufacturers will tell you that you should derate all fuses by at least 25%. So if you need 1.5 amps continuous, make sure you have at least a 2 amp fuse. This is going to require bigger power supplies for that extra 25% margin. And bigger supplies, more capital expenditures to buy them, and more operating expenses to run them. And we can see, if this is our load current, excuse me, boom, boom. This is our load current, normalized, there we go. At 1 amp, our 1 amp fuse will always blow above 1 amp. So you can get a solid amp out of it, but it could be blowing as high as 2 or 3 or 4 or 5 amps, even at times as long as 10 milliseconds. So a fuse's behavior is sloppy and stressful. It's much slower than an EFuse. There is no active current limiting. There is no controlled fault time. Bust droop is likely, which is more stressful on the supplies and the load. You've got higher I²R losses because of the higher resistance, and much higher trip currents for a fast trip. After the overload, there's no automatic reset. The system is down. Something must be repaired, and that costs money, might be truck rolls or unhappy customers. So our summary: fuses are slow, lossy, inaccurate, and they're designed to fail. On the plus side, they do protect the load, and most of them are rated by the safety agencies, so they can provide you with safety compliance. And they do excel in some applications, as we have found on the World Wide Web. Thank you very much. Look forward to seeing you for the next video.